Well, first of all, I would like to thank the organizers so much for putting on this meeting and also for inviting us to come and present. I should say this work is presented by me, but many aspects of the work are done by people who are listed here. Enrolled trilobites are iconic fossils. They're appealing because they're obviously arthropodal, but they're also intriguing because they are extinct animals. But they're also important from an evolutionary perspective for a number of reasons. Firstly, this kind of posture is obviously not the normal life posture for trilobites. They lived outstretched, and the appendages interacted with the environment. And so this particular posture then clearly has some particular function, and it's uncontroversial that it's related to enrollment, encasing the soft tissues inside the hard exoskeleton. And this is fortunate because so many characteristics of both fossil and living organisms are difficult to interpret in adaptive terms. The structure of the trilobite exoskeleton, therefore, is the very material that is providing the defensive function. I mean, what's actually preserved in the fossil is the material that is important for this particular activity. Also, of course, the body of the organism in enrollment such as this has to be coordinated in shape. And as you know, trilobites develop through a series of instars with the addition of segments to the body as they go through a series of molts. So this is an extraction of just a few instars during the development of a particular trilobite, but it indicates the major aspects of ontogeny. After hatching, the trilobite forms a calcified shield, goes through a series of molts to the mature form, and you can see that the cephalic region, the head region, remains constant in its segmentation. That's certainly not true for the trunk portion that sequentially adds segments. Now we know where the site of new segments are specified thanks to individualized segments. So in this mature form, you can see that it's the 6th segment in the thorax that has this remarkable individualized spine, and we can see that that first appears as the 6th trunk segment at the very back of the animal here. So this is the site at which new segments appear. Following the next molt, a new segment is added behind that. Eventually, this segment is released from the plate of fused segments at the back, the pygidium, and becomes a freely articulating thoracic segment. So during the development of this animal, if we're thinking about the development of enrollment, we're thinking about an animal which is changing its body and has to coordinate the type of variation or shape variation in the trunk region with that that's going on in the head. Also, the classic ontogenetic stages of trilobites, the transition from the protaspid stage to the meraspid stage, marks the development of articulation between the trunk region here and the cephalon. So these animals in this stage cannot possibly articulate because the exoskeleton is rigid. It's only if there is a functional articulation that the possibility of any enrollment can occur. So both the evolutionary context of the development of enrollment and the fact that we can track its development in ontogeny that is actually sampled for us and available for us makes this an interesting opportunity. And as paleontologists, of course, we're interested in evodevo, the development of ontogenies, and we are particularly interested as paleo-evodevo people at trying to understand something of what is going on at basal states. Not to suggest that trilobite enrollment is necessarily a basal characteristic, but certainly trilobites are our best arthropod record of early ontogenetic stages. Now, all this is well and good, but doesn't mean anything unless trilobites actually show some kind of variation in patterns of enrollment through time. And this is work by Jorge Esteve, who's done so much in recent years to re-enthuse people about trilobite enrollment. And it just shows a variety of different styles, of which this particular style, spheroidal enrollment, is the dominant one in later part of trilobite history. And it demonstrates the fact that there is a chronological, at least, change in the various styles of trilobite enrollment. So something is actually going on. So let's talk a little bit about that by thinking about the condition of trilobites and their possibilities for enrollment early in their evolutionary history. So here are two morphotypes of trilobite that are common in the early Cambrian. So this is the beginning of the trilobite record. On the left here, we've got a form that's about 7 centimeters long. You can see that it has a large number of segments, in this case about 25, but there are forms of this general morphotype that have up to 100 segments. Those segments are thoracic. They are freely articulating with a joint on both the anterior and the posterior side. And the pygidium, that plate of fused segments, is a tiny structure right at the back of the animal here. In contrast, over here is an eodiscid trilobite, which is about 7 millimeters long. It has far fewer segments in total, only about 12 segments, and only 3 of those are part of the thorax. The rest are part of a pygidium, which is a dominant structure in the trunk region. The segments are fused together, they lose their individualized form, and they form a structure which is of the same size as the cephalic region, and on enrollment could encapsulate during enrollment. We call this condition when the majority of the trunk is accommodated within the pygidium caudalized condition. So these are two very different kinds of pattern. Now, just looking at this sort of a morphotype, we can instantly recognize that it's difficult for such an animal to enroll, simply because the portion of the back part of the trunk is not sufficiently wide to fully encapsulate the venter, the underside of the cephalon in this form, even if it does enroll completely. And in 1988, Harry Whittington published his reconstruction of the maximum enrollment possible for a trilobite of this kind. This year, Javier, Jorge, and others described a specimen that actually takes enrollment quite a lot further than that. And you can see now, looking down, here is the posterior region of a trunk of Mammaspis that is adpressed against the cephalic venter. But you'll notice that there are a whole series of gaps here, because simply this area is not of sufficient size to effectively enroll and encompass that portion. So this is complete enrollment, but not encapsulated enrollment. The movement towards that condition may be exemplified by this animal here. These are just two morphotypes. The important feature of this animal is that the pleural region of the posterior of the trunk is much expanded here, such that when this animal does enroll, and we see it, we find it in the famous Purohosa assemblage of Middle Cambrian trilobites, it is effective in covering the entire cephalic venter. In this enrolled posture here, you see that the posterior part of the trunk region is not flexed, and Jorge has a series of specimens that are partially enrolled that suggest that during the enrollment process, flexure was concentrated in the middle and anterior parts. It wasn't an activity that took place in the posterior part of the thorax. And so therefore it was suggested that these posterior flexures may not be necessary for this function, and the loss and therefore subsequent caudalization would not be hindered by this particular activity. So that could be a step on the way to caudalization. Now we know that this trilobite already present in the early Cambrian, has a strongly caudalized form. And thanks to some very elegant recent work by Chan Jiguan and Ewan Clarkson, we know a lot about the ontogenies, earliest ontogenies of these trilobite phases. So here's a protaspid form before that articulation develops. Here's the meraspid degree 0 form, which is the developing trunk is just a pygidium. There are no free thoracic segments. The segments are large, such that this structure is sufficient to encase the underside of the cephalon. And remarkably, there are specimens of the degree 0 meraspis that show such enrollment. A 180-degree flip of the pygidium straight onto the cephalon. This is the pygidium here. This is the hinge. This is the pygidium here. And this is the cephalon in this form. There's a protaspid prior to the articulation, but in the first degree meraspid, it has achieved a size in the pygidium that's sufficient to do that. So enrollment from the very first stage onward. But this comes at a price. It's difficult to be an expanded, inflated structure in that condition. And during the subsequent instars, segments spool off the front of the pygidium, create a space here that allows the expansion of the relief of this animal along this flat articulation between the two. So it's possible to enroll from the very earliest stages of development, at least in this eodiscid trilobite. And this pattern of having a caudalized, as it were, or entire anterior parts of the body separated by a segmented region is not found only in trilobites. In the only armadillo that enrolls, you do see this similar straight suture in the shoulder region and in the hip region, and the three segments that are seen there. And when we look at some of the more derived trilobites from various different groups, bearing that in mind, we can start to think a little bit about their segmentation. So here's a Carboniferous proetid trilobite, and what you can see is that it has a straight margin to the cephalic venter, and that is matched by a very, very long pygidium, highly caudalized, that incorporates the majority of the trunk segments into the pygidium. These thoracic segments are those that make the link then between the inflated cephalon and the pygidium. This aciphid over here and a phacophid over there have, again, an inflated structure, but with a smaller proportion of the total length of the trunk occupied by the pygidium. Notice that the form of the base of the cephalon here is not straight. And since these animals lived in straight posture, this requires that if we have an arched structure at the anterior of the cephalon, we cannot match that with a straight pygidial margin. So it is required that this region must be bordered by thoracic segments, as you'll see in both of these. So this imposes a constraint on how much of the trunk region can be caudalized. This pattern is taken to further extreme in this flexicoliminid here, which places its smaller pygidium into this arch in this region here. And since it's Christmas, we have, I hope, a rather Mickey Mouse first attempt at, I'm supposed to do something here with the left click. Oh well, never mind. Our Christmas present is, don't worry about it. It was just a, oh, okay. Well, here we go. Oh, there it is. Now, this is a sort of rubberized trilobite. This is a first attempt at doing some modeling. But we are interested in thinking about trying to model how different types of trilobite articulation are occurring. And so that's a fun thing that we're beginning. So having said that then, what we see then is a variety of different styles of enrollment and a variety of different architectures that are going on in the trilobite trunk region. And what I'd now like to look into is a little bit about the controls of the development of the trunk region. Obviously, this is a complicated system. It has segmental components. They can vary in size and shape. There's variation in the allocation either to the thorax or into the pygidium. So can we look into what is controlling aspects of the development of these forms? So here I've simply plotted on the x-axis here the segment number from the anterior of the thorax towards the posterior, and here the percentage of trunk length. And let's take a Cambrian trilobite, this paradoxidid here, and simply measure the lengths, and you'll see that there's a declining relative length. That's as we would expect, because these segments at the front here have been around for many more molts than these at the back, so they're expected to be larger. However, that clearly isn't the case for some of these other conditions. So, for example, in Eretencanurus, you see similarly lengthed segments in the thoracic part, a declining length in the pygidium. And for these two up here, one is a Cambrian coronexicid, the other is a lycid, we actually see that the length of the individual segments increases as we go into the posterior in the mature halaspid form. And you'll see that here. The longest segments are concentrated in this region. So what does that mean? These segments have been around for longer, so they should be bigger. It implies, of course, that there's some differential growth rate that is occurring amongst the segments. And that's an interesting thing to look into. And so, of course, we look into it using our friend Alacopleura koenigii, which is a Silurian trilobite, about which a number of studies have been published, but they are published because this is a model organism for looking into development because of the particular circumstance that at Loženice in the Czech Republic, it's possible to collect large numbers of articulated specimens of a whole range of sizes. And so we're able then to measure the length of individual thoracic segments, and I think it's clear that this is a pattern like in that lycid, where in the mature form, which this is, the longest segment is not at the anterior-most portion of the trunk, it's to the posterior of that. So we're going to look now at the development of trunk segments from when there are 9 segments in the meraspid stage to the 17 segment stage, just before we transition into the halaspid or mature phase. So here are some of those specimens. And then the next image that's going to come up, it's a little bit complicated. There are, along the x-axis are a series of these stages, and on the y-axis is the length of individual segments, and it's graded so that those that are at the anterior, the front of the thorax, have white color, and it gets progressively deeper red as we go to the back. So let's put this up, and you can see that there are a whole load of lines representing the individual segments, but what's going on? So here you can see that the growth rate then of the leading segments is less than that of the posterior ones, and as we move posteriorly, so these lines steepen upwards, implying that there is indeed a faster growth rate for those posterior segments. And if we summarize this then, looking at the average per molt growth rate for individual segments, it does indeed increase. So how is that controlled? So there are 2 ways in which we might think that this growth control could be mitigated. Obviously, there are different rates for the different segments, or different segments are experiencing different rates. It could be because each segment has its own individualized growth rate. And so in this case, we're showing that same gradation. Let's take the 9th thoracic segment. It's growing at a rate of 1.1 per molt at the D9 stage. Let's say that that is unique to that particular segment, that rate, and so we persist with that rate up till the 17th, and it is higher than that which precedes it and lower than that which succeeds it. Now, another idea about how this might be controlled is that there is, instead of being a segment-specific control, a regional control that is constant through ontogeny, with higher growth rates at the back of the animal and declining growth rates towards the anterior of the trunk region. In this case, the 9th segment would experience this particular part of the curve here, but by the time that we get to 17 segments, we now divide that same curve more finely, with the result that the 9th segment is now experiencing this portion of the curve, a lower portion, and so its growth rate will have declined to this level. So we can test which of these two explanations, possible explanations, better approximate the data. This second being the idea of a regionalized growth field rather than a segment-specific growth rate. So we can test those two models, either using a power expression or a geometric progression from both the trunk models and the segment growth models, and we find we have to correct because we have different numbers of parameters, but we find tremendously much stronger support for the trunk growth model than for a segment-specific growth model. Very much stronger. There are two possibilities, or at least we tried to fit two possible curves to that generalized trunk growth, an exponential one and a power law, and both actually fit well to the data that we have, and we're not able to discriminate between the two of them. So how might this growth be mitigated? It is not about which particular segment you are, it's where you are in the particular growth field. It's about specification of position. And it's known that in living organisms in the cellularized environment, postembryonically, that such control is often mitigated by morphogens that can form concentration gradients and then lead to patterns which are interpreted during growth or development. Exponential and power law patterns are common morphogen gradient patterns, and we would point then to an isomorphism, a similarity. We obviously cannot invoke a particular control, but just point out that the growth gradient that we see in these fossil organisms is similar to simple growth gradients controlled by morphogens that are present in living arthropods and other animals, and thus that it is possible that this control is being mitigated by a morphogen. Of course, it's possible to interpret particular thresholds of a morphogen and have that as leading to a dramatic difference in pattern at some particular concentration, but the pattern that we see is a consistent gradient pattern similar to that in these simple morphogen gradients. I mentioned early in the talk that Paradoxides has a pattern in which the segments decrease in size regularly. That's a kind of isometric pattern. Indeed, that's present, or appears to be present, in Zhangcheng aspis, which is a late Lower Cambrian trilobite from China. But what's nice in terms of initial observations about this animal is that it seems, in terms of its spine development, to show a similar kind of pattern of shifting growth in terms of the development of the pleural spines. In the small meraspid stages, the spines are longest in the anterior part of the trunk, and progressively they sweep backwards and lengthen in the posterior part as the animal goes through its ontogeny. And so where allometries are occurring in growth fields of this kind, this is at least suggesting a similar pattern to that which is occurring in Alacopleura. So what I want to say is that the development of enrollment in trilobites is something that can be accessed. It is a multi-component system. There are all sorts of different aspects of segment form, segment size, segment allocation, and it has an adaptive context in which we can examine its evolution, which is attractive from a paleontological perspective. At the other end, there is the possibility to start trying to look into something of the developmental controls at a rather fine level. And the goal of this prospectus talk really then is to try and bring these two areas together as we have more examples of the details of development that will shed light on how these animals have evolved the enrollment patterns that we see. Thank you.